When we finished last time, we had a working scheme reader that could read sequences in the form of lists, integers, booleans, and symbols. And what we will do today is write a simple, minimal interpreter for scheme based on this data that we're getting from the reader. And we're going to start simple, and we're going to start with the primitives, some of which evaluate to themselves, like, for example, numbers. So if you evaluate a number, you get that same number. I spoke about the quote function, which gives you back whatever you give it without evaluating. So you can give it a list, and it will give you back that list. But, of course, if you do the same thing without quote, the list will be evaluated. And in this case, you get the result from the addition of 1, 2, 3. But as you saw just before, with a number, you get the number itself. So in this case, quote would give the same answer. The same is true for booleans, true and false. They also evaluate to themselves. There's also the empty list, which actually does not evaluate to itself. It does in common list, but not in scheme. So we're going to start with numbers and booleans, which should be really easy. And then we're going to look at more complex stuff. And maybe we can get an addition going. So the data structures that we have are sequences, which we won't need right now because we're not there yet. We have empty lists, which also right now we're not going to need. So the sequence was an interface for, in this case, empty lists and conses, which is what lists are made of. And then we have symbols, which we're also going to get to, but a little later. And then we have numbers and booleans, and we're going to focus on these first. So we're going to write a function called eval, which will take in a value. And right now, it's not going to take in anything else. We're going to get to what else it's going to need later, and which is going to become obvious. And what it returns is also a value for now. Let's see how far this gets us. So we said we're going to handle integers and we're going to handle booleans. So what we're going to do is, we could do this two main different ways. One way we could do it is we could implement eval actually as an interface on values, but I'm going to take a different route and I'm going to do a switch on the type of v so that all the code is in one place. So we're going to switch on v.type, and I think you can say v equals or v colon equals, and one case is going to be boolean and the other case is going to be number, and in the default case we're going to say panic cannot eval. Actually, let's say Fimit as printf cannot eval, whatever it is that's going to be there, which will be v.pr. And if we get a Boolean, it evaluates to itself, so we just return it. And if we get a number, it also evaluates to itself, so we also return it. So we're done, basically. And we should check that this is actually correct. So let's do an eval test. The read test, by the way, is not really a test. It just prints out stuff. But we're going to do this a little more elegantly. And we're going to make a function eval test, which takes let's do a string, and we're going to do the reading. And we're also going to do an expected string. And what we're going to do is we're going to say v and error is read of input. Actually, let's call it v input and v expected. Oh, but now we get into all sorts of trouble. And not sure I wanna deal with this. So the problem is now that we need to be able to compare two values for equality, which we will have to implement sooner or later anyway. So we might just get started with it. Could not read. I don't want to get into details here. Hopefully we'll never see this this message. And then we get the result, which is eval of the input. And now I don't know how Go handles equality, actually. On which the equality operator is defined. Okay. Golang equality. Go1 release notes, language specification, strings, big. Yes, I guess that's what I want. No, has strict rules what counts as equal and what even is comparable, which itself is based on assignability. Maybe it is what we want. Okay, let's take a look. Equal. Boolean values are comparable to Boolean values are equal. Yes. Integer values are comparable. Yes. Floating point values, complex values, strings values. That's good. Pointer values, if they point to the same variable. So that's already not what we want, because we want two lists which contain the same values to be equal, even if they are not the actual same lists. So for example, in Scheme there's two equality operators. There's actually, I think there's three. So there's EQ and there's equal. And equal is value comparison. So equal with these two lists should return true. EQ would not. Oh. Because they are actually two separate data structures, even though they look the same. But when we test stuff, obviously, we want this equal. So what we're going to do is we are going to augment our value interface with equal, which takes a second value and returns a bool. And now we need to implement equal on every value type that we have. So equal of other value. And now really the simplest way to do this is to cast this, or convert the other value to an empty, see whether the conversion was possible. Actually, this is interesting. What if I defined an empty function that also took something as an argument? Would it know whether I wanted type conversion, or would it complain? I don't know. We'll see what transpires. And they are equal if the conversion succeeds, because there is only one way you can have an empty list. Then we have conses. Oh, by the way, this was, yes, empties are by value and conses are via pointer. Equal. Did I call that equal up there? I called it equal, yes. Equal to another value. And I'm going to say C, okay, cons, but I need to cast it to a pointer, right? I hope that works. If it does succeed, if it doesn't succeed, then we're definitely not equal. If it does succeed, then we need to check whether the car and the kudar are equal. So return car.equal. Oh, this was stupid. Let's call it C's cons. Let's call it other C. No, I don't like that. OC, okay, this is stupid. Whatever, CC. So we have our car. Is our car equal to the other car? And our kudar equal to the other kudar. So that is that. Then we have symbols. Symbols are equal if their names are the same. So S symbol equal other val bool SS okay is symbol of other. If not okay, return false. Otherwise, return s.name equals ss.name. Numbers are equal if their contents are equal. Like if their actual numbers are equal. Other val bool. And then okay, number of other. If not okay, return false. Return n.i equals n.i. And And same for booleans. Boolean of other, and we call it bb, and if b dot b is bb dot b. Hooray for good names. Okay, so now we can compare for equality two scheme values. And so we just evaluated the input, and we have the expected output. So we can say if not the expected dot equal with the result, then we're just going to panic. Limit as printf eval of is not equal the expected result. So this is the input, and let's v equals, so eval of blah blah is blah blah, which is not equal blah blah. So eval of the input is the result dot pr, which is not equal to the expected dot pr. And that is the eval test. So now we can go about it and say 1, 2, 3 should be the same as 1, 2, 3. And true should be the same as true, and false should be the same as false. Oh, sorry. True. And let's see whether that works. Oh no, wrong window. Of course that didn't work. Scheme.go 36 cannot convert other type val to type empty. Why is that the case? Assignment count mismatch. Cannot convert other to type cons. Invalid indirection of cons other. C.cudar equal undefined. Oh, okay. That makes sense. Cannot convert other to type symbol. Need type assertion. I thought that was a type assertion, what I've been doing. Oh, no. Type assertions. They are not what I thought they are. Yeah, I had the syntax wrong. Okay. So it's actually other dot empty. So now my question answered itself. So it's other dot star cons, other dot symbol, other dot number, and other dot boolean. And I should actually use go run scheme.go here. Okay, impossible type assertion. Empty does not implement val. Really? Have equal. Oh, okay. That makes sense. Too many are yes. Correct. Cudar equal undefined. Seek has no field or method equal. That is also true because we haven't put equal into seek. So seek also implements everything that val implements, because every seek is also a val. And we should we should actually, if it does succeed, then we should print something to the effect that it did succeed. Printf, I guess, eval of, let's just make this nicer, like we did down there. Eval of something goes to something, and what that is eval of the input.pr goes to the result.pr, and that is what we want. So there we go. Eval of 1 to 3 is 1 to 3, eval of true is true, eval of false is false. Okay. Now, we have symbols and we have lists, essentially, and they are kind of related because when you call a function, the function is usually in a symbol, like plus is a function, although Scheme calls it a procedure, that is bound to a symbol, which is the symbol plus. So this evaluates to this. And the binding happens in a thing called an environment. And we're going to have to see how these environments work in Scheme. But first, we're going to do a different thing and implement at least one control construct, namely if. Now, I've showed you if last time. If true 1, then 2. It looks like a function call, but if is not actually a function. If is a so-called special form, just like quote. Actually, we should implement quote as well. It's not a function because in function calls, every single argument of the function is evaluated before the function is called, because Scheme is a so-called eager language as opposed to lazy languages like Haskell, in which that is not the case. In Haskell, you could actually implement if as a function, and you can check that it's not a function by saying if, and that tells you it doesn't know what to do with if. So we're going to implement if first because we don't actually need environments to do it. So we can push that back a little. And so the way if works is it takes 2 or 3 arguments. We're only going to implement the 3 argument form. The first one is the condition, which is evaluated, and then if it's false, it returns its third argument, 4 in this case, or let's use a symbol. Here we get false. And if it's anything but false, like 1, 2, 3, it evaluates its second argument. And so that's what we're going to do. But now things become a little bit more complex because we need to have a handler for for lists, essentially, or as we call them, seeks or sequences. So we won't actually work on the actual implementations of seeks, namely empty and cons, but we're going to work on the abstraction itself, and the abstraction contains enough to make this work. We can check whether it's empty, we can get its first value, and we can get the rest. And we're going to use all of that to great advantage. So if we have a seek, the first thing we want to get is its first value. And actually, what do we do if we can't get the first? Oh yeah, okay, we just panic. So we don't really care about error handling, which is of course very, very bad. But we're going to assume that the program is correct. So what we can do is we can get the first, let's call it head is v dot first. And so now we have a value, and we can switch, I guess, on the type of that value that we get on the head. And if it's a symbol, then we can check which symbol is it. So we will switch on the h, I guess I'll just say head dot type. And if it is a symbol, if it's anything else but a symbol, we cannot handle it right now. We will be later to some degree. Cannot handle non-symbol let's just call it invocation. I'm sure there's a Lispy name for it. So let's format this in a nice way. Format as printf. And that is head.pr. And if it is a symbol, then we're going to switch on what the symbol is. So now we have to switch on symbol.name. This is getting very, very deep and a little uncomfortable, but we're there. So we're going to handle if, and we're going to handle quote. And everything else we're going to say we can't handle right now. Panic, format, printf, cannot handle, invocation, off, symbol.name. Now, if it's an if, we want to get the next three items in the list, but we don't want to write the whole rest and first thing, so we're just going to make up a function. We're going to call it get3, and we're going to say condition, consequent, and alternative is get3 of v.rest. Right, so v was our seek, and v.rest is everything but the head. And with quote, I guess all we need to do is the quotee, I guess, is get1 of v.rest. And now we need to figure out what to do. So what we said before is what you do is you evaluate the condition. So we evaluate the condition, we get back the evaluated condition, so vcond, and if this is false, we evaluate the alternative, and that's the result. Otherwise, we evaluate the consequent, and that's the result. But it's kind of weird to have a function that checks whether something is false. So we're going to call it if is true vcond, then we return eval of consequent. Otherwise, we return the evaluation of the alternative. And note how, if I put this in here, this is pretty much the if in Go that corresponds to the if in Scheme, except that it has eval all over it. Of course, I forgot is true. And now all I need to implement is get3 is true and get1. But that should not be hard. So we're going to make a function called func get1 of sseek, which returns just one value. And the one value is actually just s dot first. And then we have get3 of aseek, which returns 3 values. And it's going to be, let's actually call it, I wonder whether I should do a get2. No, that's kind of silly. Let's just call it v1 is s dot first, s equals s dot rest, and then v2 equals s first, s equals s rest, v3. But now, well, we can still do s rest, but what we should do is we kind of want to make sure, even though we don't do error handling properly, that we don't get any stray arguments. So essentially that quote really only gets one argument and not 5. So what we're going to say is v is s first, and if not s rest. Did I call it empty? Yeah, it's called empty dot empty. Panic. I guess too many items in list. Let's call it seek. But I'm not going to go into specifics. And I do the same here. And then I return v. And here I return v1, v2, v3. And then I still have, we have the booleans here, so I guess I should implement it here. Func is true. And again, I could implement this in the interface, but it's a very short function, so I'd rather not do a whole lot of separate method implementations when essentially all I need to do is check, is it a Boolean, is it false? If yes, then it's false, otherwise it's true. Right, so I have vval bool, and all I need to do is b okay is v dot boolean. If it is a Boolean, so if the conversion went correctly, then I return b dot b. Otherwise, I return true. Now note this looks weird because there's no false in there, but the false comes in when it is a Boolean and the actual value of the Boolean is false. So now we have our is true. Let's see whether it compiles. No, it does not compile. Symbol.name. Really? Where is symbol defined? Symbol.name. Type symbol has no method name. Well, I didn't. Type symbol. Oh. Oh, of course. Head.name. Symbol.name, same thing. Head.name. Missing return at the end of function. I do the default. Okay, I guess I do the default here. I do the default here. So I always handle the defaults, and I return here and I return here. But I guess Go doesn't know that panic does not return. So I'm just going to return. No, well, there's no point panicking because it's not going to, should not be reached. Just to make sure that I'm not missing anything. Oh, interesting. Did I not handle a case here? So I'm switching on the type. I'm returning here. I'm returning here. Here, I'm switching again. Oh, of course, I'm not returning from quote. We haven't implemented quote, but quote is easy because I get one argument, and that's the thing that I'm supposed to quote, and quoting just means returning it. So I just return the quotee. Okay, it compiles. Now let's see whether it actually works. So we should be able to do if false, then 1 else 2, and that should be 2. If, let's not do true, let's do something else. If 1, 2, 3, then 1 else 2, and it should be 1. And let's do another one. Let's do a like a nested one. Quote true, otherwise quote false, and this should return true. No, cannot handle non-symbol invocation. Interesting. Cannot handle non-symbol invocation if. What does that mean? So we get the head, and it is a symbol. Could it be that it's a pointer to a symbol for some reason? When I work on symbols, I work on symbols directly. I don't work on pointers of symbols, which I should change anyway. But let's just check. I'm not sure here. If we are a pointer of symbol, we have a pointer to a symbol. Aha. So for some reason, we end up with a pointer to a symbol. Which is interesting. Oh, look at that. We do return the symbols as pointers. Do we always do that? I didn't implement it that way. Too many items in seek. Also interesting. But okay. Where do we have too many items in seek? Let's actually check what we have here. So we have if false, then 1, else 2, 1, 2, 3. So there's always 3, right? The head V is the whole thing, and we get 3 from the rest. So I think that's the only one. Then maybe get 3 is incorrectly implemented. So we get the first one, then we skip it, we get the second one, we skip, we get the third one, and if the rest is not empty, I mean, we could print it and see what's in there. Fmet printf. Let's just say s equals s rest. s.pr. All right. Multiple value printf in a single value. Oh, of course it's s printf. Too many items in seek, 2. So apparently, for some reason, we're skipping 4 times all in all. Maybe there is a bug in the reader. Read test. Eval. Oh, read test. Oh, look at that. We have a bug in the reader. If f, so apparently we're not skipping the Boolean. So when we read the Boolean, we read it correctly, but then we skip over the f here, and we get an additional f as a symbol, I guess. So let's look at the reader. If we are at a hash, then we advance by 1. If it's end of string, then it's an error. Ah, okay, there we go. So we get the current value. We should just advance. And then we check if it's true or false. And there we go. So if it's false, we get 2. if it's 1, 2, 3, which is true, it's 1. And here we get quote of true, which is true. So quote also works. So that's great. Now let's get into more difficult territory. What we want to have is, let's just say working plus, right? We want to be able to say plus 1, 2, and we're going to get 3. And we don't yet care about implementing. We don't yet care about our own values, variables, or our own functions. We only care about the global functions that are available for us to use. Equal would be another such function. We already have an implementation, but we don't have it available yet in the language. So we're going to implement an interface that we're going to call environment, or env maybe. And what it's going to do is it's going to map from a symbol to a value. We could use the built-in map type in Go, and we will use it underneath. But there is a good reason for why we're going to leave the implementation abstract, which we'll see later when we implement more complex stuff like having your own functions, where the environment will not anymore be one flat map. So let us define this type somewhere, maybe somewhere here. So env will be an interface, and the interface will provide a function. Actually, we don't need the function. It will provide a function called, no, map is not, lookup, just lookup. And it will take a symbol and it will return a value. Actually, it should return a value and, I guess, Boolean, whether the lookup was okay. We should at least take care to make error handling not unreasonably complicated later on. And now we provide a simple implementation of the environment. Actually, I'm curious whether can you in Go implement an interface for a map type? And are maps passed by value? I'm just gonna try the following. I'm gonna say global env, and I'm gonna implement it as a map of string to value, and then I'm gonna implement on GE global env. I'm going to implement the lookup function, which takes a symbol and returns a val and a bool. And all I really need to do is do the lookup on the map, all right? So all I need to do is GE of s.name, I think. Ooh. course, I always make this mistake. Does this compile? Not enough arguments in return. What is the val v and OK? Return v OK. Does this work? It does work. Okay. So now we have the lookup. Now we need an environment in our eval function, and we will not use a global variable for this for a variety of reasons. One of them being that you shouldn't do that, and the other one being that it won't actually work when in the future we implement more complex environments. So we're going to give it an environment. Now, of course, every time we call eval, we need to pass the environment as well. And we're going to have cases later on where we're not going to pass the same environment on, as we shall see. And here, of course, we need to now make. Actually, let's first do the following. Let's first check what we want to do. So here's how evaluation works. And we've already seen this, and I mean evaluation of function calls specifically. What happens here is that what is evaluated is the symbol plus, which in this environment gives the function plus, and then 1 is evaluated, which gives the number 1, and 2 is evaluated, which gives 2. And then the result of this evaluation, which is the function plus, is invoked with these two. And that's what we're going to do. We're not going to make a special case for when the function is given as a symbol, because later on we will see that functions can be given as something more complex as a symbol. So we're going to go all the way right from the start, and we're going to make sure that we can evaluate plus to a function plus, and we're going to see how what that's going to look like. And then we're going to have a thing where we can invoke that function with arguments. But let's first do a simpler case, the case being that the evaluation of a symbol and it's going to give us a result and an OK, because we're going to look up the symbol in the environment. And if it's not OK, we're going to panic. Cannot unbound s, and the s is v.name. Otherwise, we just return the result. And we can already put this to use if we do something like, we're going to make ourselves an environment. We're going to call it E, and E is a map. How do you write literals, map literals in Go? Do you need to do make? Maps. Oh, there we go. Okay, that's how it works. So we do map of string to value. And we're gonna bind 1 to the number 1. Which is not very useful, but it will allow us to test. Actually, we're going to put that into eval test. And so here we call eval. We're going to put this environment in. And now it should be possible to write evaluate 1, and it should be 1. Can it use E as type env? Map string val does not implement env. Missing lookup. Map string val. Okay, I guess I need to convert it to global env. There we go. And 1 evaluates to the number 1. So now the next thing that we need is we need a way to represent the plus function as a value in scheme, which will require us to implement a new value type. And we can call that something like built-in. This is the seek interface, and the built-in is going to be a regular scheme value, built-in, but it's going to represent a function in Go. And to make things easier, we're going to give it a name, just so that we can print it nicely. But its main thing is actually f, which is going to be a function, and it's going to take something, and we're going to see what that's going to be, and it's going to return a value. And what it's going to take is I think the easiest thing to do is to just give it a slice of values. And now because it is a value, we need to implement these two functions on it, namely the built-in per, which returns a string. And we're actually going to use this same syntax here, except I recoil it, seeing it called procedure, we're going to call it function. So we're going to return from it printf function, and we're going to give it a name. Well, we have the name, and the name is b.name. And b built-in equal to another value, bool, and we're just going to implement identity of function, essentially. I hope Go implements that. If not, we might just return false, I guess. Actually, let's just return false. You shouldn't compare functions. Actually, no. Let's panic. You should not compare functions. But now we also have an additional thing, namely functions can be called. So we're going to make up an interface which we shall call function. And function will provide a method called call, which takes a slice of values and returns a value. And of course, our built-in supports that function, implements that function, built-in call, takes a slice of values, args, and it returns a value. And the implementation is trivial because we just need to call b.f on the arguments. And now we're ready to implement our plus function. And we're going to call it built-in plus. And it takes arguments, which is a slice of values, and it returns a value. And now, here's a nice thing about plus in Scheme. You can give it any number of arguments. You can say 1, 2, 3, and it will give you 6. Or you can just say 5, and it will give you 5. And you can even not give it any argument, and it will give you the neutral element of addition, which is 0. And that's what we're going to do. So we're going to say sum. Actually, we need to, how did we implement number as int64? So I guess I need to say var sum int64 equals 0. I guess I could also say sum equals int64 of 0. And now what I'm going to do is for how do you get the, when you do a for over the range, do you get the values first or do you get the indexes first? Let's go for key value over an array. Okay, so I ignore the key because the key is just going to be the index and the value is going to be the actual argument range of args. And now, of course, I need to make sure that it's actually a number. Arg.number. If it's not a number, then we're going to panic. Cannot add non-number s. And we're going to, of course, finite printf. Cannot add non-number s, and the number s is going to be n.pr. No, arg.pr. And if it is okay, then we just say sum plus equals, I don't know if you have plus equals in Go, we'll see, n.I, and we return the number sum. Let's see if it compiles. It does compile. And now we can add built-in plus to our environment. And it's a built-in. and its name is plus, and its function is built-in plus. Now note that we really don't have a way to read the function. So we can't really write an eval test, because what would we put on the right-hand side? We can't just write function plus there, because it's not going to read back the built-in. So what are we going to do? I guess what we could do is we could make like a special case where this is an empty string, and if it's an empty string, then we just print the result. So that's the input, that's the expected. Actually, let's move that down. If expected is the empty string, no, if expected is not the empty string, then we go through this rigmarole of reading expected and checking that the results are actually the same. Otherwise, we just print input and the result. And yes, that was a mistake. And now there we go. We evaluate plus and we get a function plus. So now we actually have two cases now here where we have a function invocation or a potential function invocation, namely here where we know it's a symbol, and here where it might be where it's not a symbol but it's something else. And we're going to handle both with the same code, and to do that we're going to write a function, and the function is going to be func eval application, and it, of course it takes an environment, and it also takes the function, which is a value, and it takes an arg list, or just let's just call them args, which is a seek, and it returns, of course, a value. So we return here eval application. In the environment, the function is the head. Of course, it's not the function yet. It will be the function after it's evaluated. So it's the f is actually the unevaluated function here. So I should call it f form, and arg forms. The head and v dot rest. And here, same thing, eval application, the head and v dot rest. And now what we do is the actual function is the evaluation of the function form in this environment. And I guess we can now check whether it's of the correct type, and the correct type being the type that we just defined, namely the interface that we defined, namely function. So, stupid value names, stupid variable names. Let's call it vf, and this is f. OK is bf.function. And if it's not a function, then we panic limit sprintf cannot apply to non-function. Actually, can apply non-function. And the non-function is fform.pr. No, it's actually not. It's f.pr. That's the function. Fform is what evaluated to the function. Otherwise, we do have a function, but now we need the arguments. So we're going to say args is an empty slice of values. And we're going to say for as long as not arg forms dot empty and as long as argforms are not empty, we get an argument which is argforms dot first, and we evaluate it. So that's not the argument, that's the argument form, and the argument is the evaluation in our current environment of the argument form, and we append it. So args equals append args arg, and we return args. No, we don't return args. Now we must call the function. So we return f dot call args. And I think that's it. Does it compile? It does not compile. f.pr because it's a function vf. Okay. Now let's see if we can eval test plus 1, 2, 3, and that should be 6. Interesting. So what's happening here? For some reason we're looping endlessly. Why is that the case? Oh, of course, because we never advance. Argforms equals argforms.rest. That was easy. Ta-da! And there we have our addition. Now, let's do another fun thing. Let's do multiplication, and then we're going to see how to make a function application where there's not actually just a symbol in the function position. So where do we have our built-in plus? So we're going to do built-in mult, or mul, I guess. And this is the product. And we could implement this with a higher order function, but I'm too lazy. The neutral element of the product is, of course, 1. So the product times equals the number. Cannot multiply non-number. And we return the product. And this is star built-in mul. Now let's just check that it works. Eval test mul 3, 4, it should be 12, I think, if my math is right, and it is. But now, look at this. If true, then plus, else, mult. 3 and 4. This should give us the addition, because true is true, of 3 and 4, the sum, which is 7. But if this is false, it should give us the multiplication, the product, which is 12. And indeed it does. And that's it for today. And next time we shall actually look at how to implement our own functions in our little language.